Welcome back to another video. It's your favorite math professor here, Dr. Tarcia Hubert. And in this video, we are going to talk about the distribution of the sample mean. And so what exactly is a sampling distribution? I'm glad you want to know. Well, it's a probability distribution for all possible values of the statistic computed from a sample size of n. So now you're creating a probability distribution based on a statistic. That could be any statistic you're interested in. It could be the mean, it could be the standard deviation, it could be the median, it could be a proportion. So basically you're taking and making a probability distribution based on that statistic with a specific sample size, okay? So each of these has one specific sample size. Now in this video, we're going to talk about the sampling distribution of the sample mean. So the probability distribution of the sample mean is one in which all possible values of the random variable x bar, that's our sample mean, computed from a sample of size n from a population with mean mu and standard deviation sigma. So that's our population mean, mu, and our population standard deviation sigma. All right, so the sampling distribution of the mean of the sample mean is going to be every possible value for the sample mean from a certain population with a certain sample size. Okay, so the idea of that is you obtain a simple random sample of size n from your population, and then you compute the mean. And then, assuming that your population has a finite number of individuals in it, you're going to repeat steps 1 through 2. And that means you're going to keep taking a sample of that size, of that sample size n, and you're going to compute the mean. And you're going to do that for all possible values, and then you're going to create a probability distribution based on that. All right. Now, whenever you create this distribution, it can be normal or it cannot be normal. So normal, remember the curve looks like this, is bell-shaped, or if it's not normal, that means it's skewed in one direction. So this one is skewed left and this one is skewed right because the tail is to the right. However, or let's look at an example. Then I'll tell you about the however. So example, an intelligence quotient or IQ is a measurement of intelligence derived from a standardized test, such as the Stanford-Binet IQ test. Scores on this test are approximately normal. So this is the population. This is describing the population. It's normal with a mean score of 100 and a standard deviation of 15. What is the sampling distribution of the sample mean for a sample of size n? All right, so this is the idea. You take a random sample of 9 individuals and you record their IQ scores, and then you find the average, and that will be your sample mean. And you just keep repeating this process and find the average, right? And you just keep repeating it. And then what you do is so looking at the graph on the right, is you create a histogram of each of the means. So this is going to be every possible mean and the frequency of that mean. So how many times that mean shows up, all right? Now this graph to the left is the graph of the population. They said it was normal with the mean of 100. So your mean of 100 is in the middle. Now, notice that this is the graph of the sampling distribution. It still has a mean of 100, all right? And its standard deviation is 5 right here. And this is saying n is 1,000. That means it repeated that process 1,000 times, okay? Now, notice that the shape of this graph is also normal. It's normally distributed. So what we can conclude from this is that if the shape of the distribution of the population is normal, then the shape of the sampling distribution is also going to be normal, okay, for the mean. The shape of the population is normal. The shape of the sampling distribution of the sample mean is also going to be normal, all right? Also, we can conclude that the means are equal. You see the mean here is 100. The mean here is 100. So the mean of the population is going to be equal to the mean of the sampling distribution of the mean. All right, and recall that it also said that the population standard deviation was 15, and this standard deviation is 5. So this standard deviation is lower than this. And you can also tell by the shape of the graph, the lower the standard deviation, the higher the peak is going to be. So this one has a higher standard deviation, it's more spread out. This one has a lower standard deviation, it's less spread out, all right? So we can draw some conclusions if we know that the population is normally distributed. So first of all, the shape of the distribution of the sample mean is also going to be approximately normal. And then the center is going to be the same, meaning the mean of the population is also going to be the mean of the sample of the sampling distribution of the sample mean. And then also the spread, okay? So the standard deviation of the sample mean is going to be less than the standard deviation of the population, all right? So that's three things we can conclude if we know that the population is distributed normally. So if we were to repeat the problem in the previous example with a sample size of n equal 25, so remember last time we did it had a sample size of n equal 9. Well, now do it, but this time you pull 25 people and you take their IQ score and you calculate the average, and then you just keep repeating that process. You end up with a sampling distribution that looks like this. So as you can see, it's still normal because remember our population was normal. Our standard deviation, our mean is still 100, so the mean is still equal. And our standard deviation has gotten even smaller. So it was 5 when n equal 9, and now it's 3 point something with n equal 25. So in addition to what we concluded before, we can also conclude that as the size of the sample n increases, the standard deviation of the distribution of the sample mean decreases. So as your n gets bigger, the standard deviation is going to get smaller. And this is how you find the mean and the standard deviation of the sampling distribution of X bar. So the mean of X bar is going to be equal to the mean of the population, and the standard deviation of X bar is going to be equal to the population standard deviation divided by the square root of n. And then there's another name for the standard deviation of the sampling distribution. It's also called the standard error of the mean. So the standard deviation of the sampling distribution of X bar is also called the standard error of the mean. All right, now you can also sample from a population that is not normal. And in this case, the mean of the sampling distribution is still going to be equal to, I don't know why they move like that, but the mean is still going to be equal to the mean of the population. And the standard deviation is still going to be, it moves right here, I don't know why. But the the standard deviation is still going to be equal to the population standard deviation divided by the square root of n. So hopefully y'all can see it right here. If only I can pick it up and move it right there. But that's where it's supposed to be. Let me go back. And then number 2, the shape of the distribution of the sample mean becomes approximately normal as the sample size n increases regardless of the shape of the underlying population. So if your population is not normal, then your sampling distribution may not be normal, but you can make it normal by increasing your sample size, all right? And that leads us to the central limit theorem. And the central limit theorem says regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size n increases, all right? So it may not be normal, but if you increase the size of n, you can make it approximately normal, all right? And so here's an example. Here is a population in A, and this is the shape. You can see it is not normal. It's definitely skewed right. But if you take the sampling distribution with n equal to 4, you can see it's not normal because there's a longer tail on the right, so it's skewed right also. However, it kind of looks close to normal, but it's not. And then if you increase the sample size to n equal 10, it's still not normal because there's a longer tail on the right. It's skewed right. And then if you increase the sample size to n equal 25, it becomes more normal. So it's approximately normal here. And you can look at the tails and see they're almost kind of the same. But this is just a demonstration of as you increase the sample size, the shape of the sampling distribution will become approximately normal. Now the magic number is 30, okay? So if you increase the sample size to 30 or more, it'll be approximately normal, the shape of the sampling distribution of X bar. So let's look at an example, all right? In this example, the length of human pregnancies is approximately normal with mean mu equal 26. So this is telling us that our population is distributed normally, all right? With the mean is equal to 266, and that's the population mean, and the population standard deviation is equal to 16 days. And we're going to answer some questions. The first one is, what is the probability a randomly selected pregnancy lasts less than 260 days? So right here, all we want to know is, what is the probability that X is less than 260? That's a less than sign. That X is less than 260. Now, in this case, since the population is normally distributed, and we can standardize this by finding the z-score and then using our z-chart. So remember that z is equal to X minus the mean, oops, that should be 260, is equal to X 260 minus the mean, which in this case is 266, divided by the standard deviation, which is 16. So 260 minus 266 is negative 6 over 16. And when you divide that out, you end up getting negative 0.375. And remember, our Z chart only goes to the hundredths place, so we're going to round that to negative 0.38, okay? So that's our Z value, and that's what we want to use on the chart to find the probability. And so remember that the probability gives us the left end of the tail. So if the mean is here, 266, 260 is going to be about right there. So we're looking for the probability under the curve, or the area under the curve here, if this is 260. And remember, our Z chart gives us the tail to the left. So that's exactly what it will give us. So now let's go and look at our Z chart for negative 0.38. So here's our Z chart. Remember, it gives the left tail. Negative 0.3 is here. And if I go all the way down to 0.38, I get 0.3520, and so that will be the probability. So if I go back here, the answer will be 0.3520. So that's the probability. And basically what that means is that if we select a simple random sample of 100 individuals, of 100 human pregnancies, then about 35 of those pregnancies will last less than 260 days, okay? So now it wants us to answer this part. Suppose a random sample of 20 pregnancies is obtained. Describe the sampling distribution of the sample mean length of human pregnancies. All right. So since we know that remember that the population is already distributed normally, then we also know that the random sample, the sampling distribution of the sample mean is also going to be distributed normal. So it's going to be a normal distribution, and that's because the population is distributed normal. If the population was not distributed normal, then this sample size of 20 would need to be bigger than 30 or bigger, all right? Also, we know that the population mean, the mean of the sampling distribution is equal to the population mean. So our mean of our sampling distribution is also going to be 266. And then the standard deviation of our sampling distribution is going to be equal to our standard deviation of the population divided by the square root of n, which is 20. So if we do 16 divided by the square root of 20, we actually end up getting that to be approximately, let me change this to squiggly line, 3.5777, but if we round it to 3 decimal places, it'll be 3.578. So that would be the standard deviation of our sample mean. All right, for this last part, we want to know what is the probability that a random sample of 20 pregnancies has a mean gestation period of 260 days or less. The difference between part C and part A is we have a sample size of n equal 20. That means we're going to be taking the sampling distribution of the sample mean. And so since this, we already know it is distributed normally, we can standardize this 260 by finding the Z value. So 260 minus our mean. We're doing the mean of the sampling distribution for the sample mean, which is 266, divided by the standard deviation of the sampling distribution for the sample mean, which we said was 3.578. So if you divide that out, you end up getting Z to be negative 1.68 if you round it to the nearest hundreds. And so we want to go to our chart and find what is the Z value for negative 1.68. Negative 1.6 is here. Go all the way down to negative 1.68 and you get 0.0465. So I'm going to go back and I'm going to say this is 0.0465. I don't know why I started writing it in red, but that would be our probability. The probability that that it's going to be less than 260 days. So what does this mean? This means if we take 100 simple random samples of size n equal 20 human pregnancies, then about 5 of the samples will result in a mean gestation period of 260 days or less, all right? So this is how you would work that. As an example of using the sampling distribution of the sample mean. If you have any questions about anything I did or said in this video, please let me know. Thank you for watching, and I will see you in the next video.